So today's lecture we are going to discuss about asynchronous circuits. What we will do is we will define how these asynchronous circuits are built and also take a simple example to show the design of the asynchronous circuits. The other problems associated with design of asynchronous circuits, and we will follow it up in the subsequent lectures. These are asynchronous sequential circuits, and if you talk of sequential circuits, the fundamental property of the sequential circuit is that the present output is a function not only of the present inputs but also a function of the past inputs. So previously, in case of synchronous sequential circuits, we discussed how the past history can be captured in terms of a state of a machine. And the fundamental thing about synchronous sequential circuits was there was a clock, and each time this clock appeared, you transferred the next state into the present state. So the clock was the timing which was responsible for transferring. So that when we talked of st plus 1 and st, this relationship of t plus 1 and t was established through the clock. That is, the present state, the next state will become the present state once the clock comes. When we talk of asynchronous circuits, there is no clock. That is a fundamental thing. So we do not have a clock as an input over here. But the other property, sequential circuit property, remains. That is, we are talking of the present output being a function of not only the present input but also the past inputs. Now, how is the past input captured? The set of past inputs that are there is again a notion of a state, but here the notion of the state is little different from the way we understand state in the synchronous sequential circuits, and this is important to realize. So when you talk of asynchronous sequential circuits, the changes are to be initiated only by the change of inputs. This is again different. In case of synchronous sequential circuits, the changes could have been initiated just by a clock. A clock could take, for example, something like a counter. A clock takes it through various states without, you may not even have an enable count as an input, even that may not be present. Still it will go through and the clock will be responsible for doing that. But in case of asynchronous sequential circuits, all changes are initiated only by the change in inputs. So we refer to this as an input state. Of course, there could be multiple inputs, and this is called the state, input state. Whatever is the input, the values, all the inputs together, they constitute a state of the machine. So basically, as far as the input state is concerned, if you have, let us say, 3 bits of input and 3 bits can take all the possible 8 values, then you have 8 input states corresponding to each other. But if you have more restricted, let us say it is a BCD input, though there may be a 4-bit binary input, but because it is a BCD input, there are 10 possible input states. These are the possible permissible combinations of the input which constitute the input state of the machine. Now, we also have, but of course, after all, the past history has to be somehow to be captured, because that is how the past, after all, the present output is not just a function of the present input, but it is also a function of the past input. That is captured through what is called a secondary state. It is also referred to as an internal state. So these are basically, both of them are synonymous. Some authors like to use the secondary state terminology, sometimes some people use the internal state. So this is the secondary state that we have. Again, it could be multiple number of bits. These two together, that is a particular combination of the secondary variables or internal variables, these are the y's, and a certain combination of the input variables which corresponds to the x, they constitute the total state of the machine. They together constitute. So if you look at this, so this is together constitute the total state of the machine. So now what happens is, given a certain state, state transitions can only be initiated by change in inputs, that is very clear. So now given a certain state, we will go to a next state. But this particular state change will happen through what is called the excitation variables. These excitation variables, so they are just like the next state. You had the notion of the next state in the synchronous state machines. But the difference is, we are presently assuming that there is a delay. So now there is no clock here. This is just a delay in terms of, we can consider this to be some delay, after which this excitation input will actually become the secondary state. So this delay is present, and so this delay will generate this. But what happens over here is, because there is no clock, this loop is not broken, this change could actually result in so this change could result in something else, because after all, now after a certain delay this is going to become this, and this was different from what was originally y was there, the small y was there. Then this particular combination of secondary state and the input state could result in some other excitation, and this can sort of circulate. But what we assume is it will reach a certain state of equilibrium. Our design has to ensure that it should not go into what's called oscillations. It should, after some time, after going through some transients, finally we will reach a stable secondary state, and that stable secondary state is nothing but y is equal to y. This is the stable, because what happens is, once you reach this, then no amount of change, because this particular change will initiate this, but this is actually the same, and so then this transitions will come to a stop. So these transients will die down and we will reach an equilibrium state, and that is now actually the secondary state, which is a stable secondary state. And now our machine reaches a stable total state given by the input state and the secondary state. Now the problem is, when I consider such a situation, things get more complicated if I permit multiple inputs to change simultaneously. So a very simple assumption that is made is, typically such designs are done with what's called fundamental mode of operation of the circuit. The fundamental mode of the operation of the circuit refers to the fact, of course, if there is only one input, then there is really no problem, or the circuit will be in permanent state, except that I will define there something more. Once an input change occurs, first of all, only one input can change at a time, that is one thing. Second, if one input changes, then it is going to result in some transients, and then the next input change is not going to occur till we reach an equilibrium. During the time these transients are coming, we will not change the state, because then the design becomes extremely complex. You will see that even with this assumption of fundamental mode, the design is considerably more complex than sequential circuits. But now in real life, how will it work? In real life, the way it will work is, we will do the design with fundamental mode, but also try to examine what really happens if more than one input changes occur in the actual implementation, to make sure that nothing drastically goes wrong. But otherwise, our inputs can also be ensured that they actually do not change, more than one input does not change at a time. There are mechanisms of establishing that. So we design the circuit in the fundamental mode. To define it again, what we are referring to is, only one input change will occur at one time, and no subsequent changes will occur till all these transitions die down and all these transient die down, and we reach an equilibrium state. And that is the assumption of fundamental mode. Now what is this delay vis-a-vis, let us say if you talk of a synchronous circuit, we had the state register, but what do we have to do to implement an asynchronous circuit? In case of asynchronous circuit, fortunately, we do not really need any component to give a delay. See, when you talk of a combination logic, if we talk of what we are doing is, if you consider any particular gate, I can break down this gate into two parts. This particular gate also has some delay. Let us say it has a 3 nanosecond delay. I can break it down into this followed by 3 nanoseconds. That is an ideal AND gate which has 0 delay followed by a 3 nanosecond delay. So this is a very notional breakdown. I do not have to design anything. So what happens is, this particular combination logic has a certain delay associated with it, because after all, any circuit that you build is going to have a delay. Typically, that delay is sufficient to ensure this. So we do not really need any component to do this. So as far as your description of the circuit is concerned, we show it as separately as a delay as a component, because on the feedback, you can assume that this is an ideal logic block which has no 0 delay, and then I have the delay of this extracted out and put in the feedback path. Of course, there are issues regarding this, because the delay is not going to be identical if the paths are not going to be identical. This issue is going to be more important when I have multiple y bits. So there are issues design issues which come because of that, and we will consider that in the next class. Right now we are not bothered about it. What we say is all the delay is concentrated over here. This is an ideal block, and whenever an input changes, it will set off some transients here, and these transients will die down in due course of time, and we will reach a next stable state. And no input change is permitted till then, and once again the input changes, I will repeat this process. So let us go through the example of doing a design of an asynchronous sequential circuit, and here we will use a very simple example to do this. The example is like this. I have considered a circuit with two inputs x1, x2 and one output z. The output is 1 only when x1 and x2 are 1, with x1 being 1 first. That is a difference. What I am trying to say is there are two inputs x1 and x2. So if you consider from the block point of view, block diagram of that, so I have x1, I have x2 and I have z. There is no clock, please remember, and z is going to be 1 when x1 and x2 are 1. If this is my only definition, then it is a combination logic, because I do not need the history. If I just say z is going to be 1 when x1 and x2 are 1, you know the implementation is a simple AND gate. But what I want to also know is which one actually became 1. How did it reach the present state? Well, did the x1 became 1 first or x2 became 1 first? If x1 became 1 first, then only my output is 1. If x2 actually became 1 first, then my output is 0. And because of it, it is a sequential circuit and it is not a combinational circuit, because of the fact that I cannot just look at the present inputs x1 and x2, present values of the input x1 and x2, and say what the output is. I also have to look at the history of the inputs, and that makes it a sequential circuit and not a combinational circuit. So once I have this as a sequential circuit, I can draw a waveform of this. This is a very simple waveform, so I can draw this. I start by drawing x1 and x2. Of course, I should try to make sure that not just all possible combinations we do only in case of combinational circuit is sufficient to do all possible combinations. But these waveforms have to be so drawn that it takes care of all possible situations that can occur here. That means also the history of inputs, the variety of history of inputs that can come. As far as this problem is concerned, the variety of inputs is only 2. That is, how did you reach 1, 1? Whether you reach through x1 being 1 first or x2 being 1 first. Please remember, this is a very, let us say, this precisely defined problem only because we do not allow x1 and x2 to go 1 together. They cannot change simultaneously. Whatever may have been their previous value, they have to change 1 at a time. That is a fundamental mode of operation for the circuit. So now I have this 0. I have.
So isn't it similar to a problem with pattern matching when we are having just one input and seeing just two last inputs?
No, not one input. So now we are talking of two inputs. So it's not, when you talk of change the number of inputs and their timing relationship, there is no direct equivalence to there. But you can actually say that you can, with two inputs also, you can say that you are looking for a pattern. The pattern that you are looking for is a, let us say 1 0 followed by 1 1. So there is a method of modeling it and implementing it as a sequential state machine. See, all these things that we are doing over here, you can also do it through a sequential machine, except that you will be doing a synchronization with the clock. That is, when you start implementing a synchronous sequential machine, what happens is input changes are not important within the clock. That is, within a clock, let us say an input changes twice, you are still going to make only a transition corresponding to the last input change. Let me illustrate this point because this question has come up. if I have this as my clock and my input changes over here, I am, let us say, going to make a transition at all the rising edges. This input change will be completely ignored in case of a synchronous. If I have mealy machine, of course outputs may change. Temporarily the outputs may change, but the state transitions, these input changes are not going to be captured in terms of the state of the machine, because the state transition is only going to occur over here and it is going to only sense that it is actually 1 over here. The fact that it was 1, a 0 and a 1 is going to be completely ignored, because all of this happened within the clock period of the. So that is the typical model of a synchronous sequential machine. In an asynchronous machine that will not happen. Whenever an input change occurs, it will be reflected in terms of that. So if your inputs are going to change rather slowly and you in relation to the clock, all this slow and fast is typically relative. If they are going to change slowly in relation to the clock, that is multiple number of times inputs do not change within a clock. So it is actually possible to implement all these designs using a synchronous model of the machine, except that you will be synchronizing the state transitions to the clock. The inputs may be changing at odd times, but you will synchronize them to the clock. So generally many situations that is not really a big issue. But asynchronous machines, we will point out at the end of this class that they have a certain distinct advantages, and in some situations they are used. Though the reason they are not used much more widely is the design is not easy. The design is complex, and also ensuring that it works properly is also not, takes much more effort. Okay, so now I have my input changes. So what I have is x1 and x2. x1 has a waveform like this, x2 has a waveform like this. Now if I look at z, z is going to be 0. Anyway, z is going to be 0 when x1 and x2 are 0. There is no question about it. When x1 goes 1 and x2 is remaining 0, z is 0, but now it is now. So again this part also the z is 0, but once this goes 1, then z is going to change to 1, because both of them are 1 and x1 became 1 earlier, and these are the condition for z to be 1. So this will remain a 1, but once this goes to 0, now x1 has gone to 0, so this will, z will go to 0. Now x2 has also gone to 0. So all these input changes are going to mark the boundaries for me. So this is going to be 0. Now this becomes 1 and this actually remains 0. Now both of them are 1, but because x2 became 1 earlier, so this will remain 0. So these are let us say in terms of the timing, you can draw these waveforms. From the problem definition, a waveform like this can be drawn. Of course, when you are drawing the waveform, you should be clear that you are taken care of the situations that you need to capture. The situations here you need to capture is the fact that x1 changes first and you reach both 1 1, and x2 changes first and you reach both 1 1. Now once I have done this, then I can identify the states of the machine, the total states. Remember, the total states are two components. The total state has the input state as well as the secondary state. Both of them together constitute the total state. So now actually to each of that regions that we identified, I will have one stable state. I should have also drawn a line here. Okay. For example, in this region I define one state, I call this state 1. Please remember, this is not just a secondary state, this is the total state of the machine. Okay, so we will see that how this state is going to be composed. So this is the reason I call this as a stable state is, if no input changes occur, nothing will happen to the circuit. That is the definition of this. If no input changes are going to occur, if the inputs are going to be x1 and x2 for does not matter for how long, this z will also remain 0, these two will remain 0 and nothing will happen to the circuit. But now I change x1 to 1 and now I am going to go into a stable state called 2. I may go through some changes in between, we see that later, but I will be in stable state 2. Now this change occurs, I go to stable state 3. I get back to 0, x1 gets back to 0 and I go to stable state 4. x2 gets back to 0. Now both of them are 0. I do not need to differentiate between this stable state and this stable state. That is the most important thing. Once I reach 0, that history need not be captured. It does not now going to matter that when I am going to go to the output, it does not matter how I came there. So this is this numbering of the states is important because you should not have too many states than what is required, because basically remember the problem like the even odd problem. You needed to capture only the fact that when you are doing a synchronous state machine, you only needed to capture whether how many ones till now were even or odd. You do not have to keep on storing all the ones. Similar situation exists here. Once you reach this 0 0, I am marking this stable state as same as this one, because everything else is now going to be exactly identical as I was before. Now when I go to this particular stable state, next stable state, so I am marking this as 4. The reason 4 is, please remember the input state has to be the same. Input state is x2 is 1 and x1 is 0 in 4 also and in this also. And again I do not have to distinguish how I came, I do not have to remember what was their history of this before, and that is why I am going to be in 4. But once I come to this 1 1, when I am coming from x1 0, x2 1, I will not go to the stable state 3, but I will go to a stable state, though this also corresponds to, in terms of this region and this region, both of them the input state is same, but my stable state that I am going to reach is going to be different, because first of all my output is different, and in some cases the output may not be different, you may still need to differentiate, but not in this problem. But in this problem you do have to differentiate between this 1 1 and this 1 1, because any time inputs being same and output being different, the distinction can only come from where? Look at this block. If output has to be different and for the same set of inputs, the only differentiation can come from the secondary variables. The secondary state has to be different. The secondary variables have to define the output change. So in this case, the inputs are same, the primary inputs are same, and the output is different. So it is a different stable state than this. And once I go to, okay, I should have drawn another line here, my mistake. So once I go to this 1 and 0, what will be the stable state here? I do not have to distinguish here, because anyway y1 x1 is 1 earlier, then x2 is 0. So when I am 1 0, so I can actually go to stable state 2, but actually I go to 0 0 here and I go to 1. So given a problem definition, this particular waveform and marking of these stable states is the starting point. Once I have marked this stable state, actually I can convert this waveform into a table, and this is called the primitive flow table. The way I convert this into a primitive flow table is, I have x1 x2 values just like in my Carnot map. I also choose a sequence which are more input states are one Hamming distance from each other. So I am in So each row I will have for each stable state. So I am in a state which is 1 with my output 0. Now my input is going to change. I am going to transform this. So if I am going, my input is going to change to 1 0. So I basically are moving from this column to this column. So I will go to state corresponding to 2, stable state 2. So this is the change. So when I am moving from here to here, I am basically inputs change, and due to the inputs the state changes. As soon as the input change, this I am moving from this column to this column. Oh, sorry, this was I should have gone to my mistake. Okay. Either I have to change this or I have to change that. So if I am writing x1 x2, so now I am initially in 1 0. Now I go to 2 0, and this particular change comes by change of input from here to here, and I move to this. I will explain to you why this movement is written in this form, and this will be clearer later. So now once I have this, the next change that I am going to is x2 is also now becoming 1. So that means I am going to go to 3 1 and this is corresponding to change. The next change that is coming is x1 is becoming 0, and so I am going to 4 The next change, as far as my waveform is concerned, the next thing that is happening is x2 is also becoming 0. So when x2 also becomes 0, I am going this. See, this is, if you look at this waveform, what are the changes that are happening? x1 x2 was both 0 0, then x1 became 1, then x2 became 1, then x1 became 0, then x2 became 0. Okay, x1 and x2 followed each other. So this is what I am reflecting over here. I started from a stable state of 1, output of 0. x1 became 1, I went to a stable state 2, then x2 became 1, I went to a stable state 3, then x1 became 0, I came to a stable state 4, and then x2 became 0 and I came back to stable state 1. So this is what it is showing. When an input change occurs from here to here, what I typically define is, I go to a transient state, because what happens is inputs has changed, but your excitation has, your secondary variables have not changed. So there is a transient state. Okay, for presently we define this transient state to be different from a stable state. So I don't circle it over here, and I call this transient state to be the same as the stable state. There will be situations where we will be making a change, and we will consider that in the next class. For the present, we say that each time we call the transient state to be the same as the stable state I am going to go. So this is my transient state, this is my transient state. And the way I differentiate between the transient state and the stable state is, I don't circle it here. Of course, my problem is not complete. I have to now, from this 0 0, if you look at the waveform, now x2 is going to become 1 first. So that means I am going to go over here, sorry, 4. So I am going to go to this particular state 4, through this particular transition, that means I will have a 4 here, and this is followed by x1 becoming 1, and when x1 becomes 1 I have this, and this is nothing but this transition, and this corresponds to a transient state of 5. Now again this is going to be followed by first x2 going 0. When x2 goes 0 I go from here to here, and this was same as, if you look at your waveforms, so that was x2 going 0 and I am going to 2, and this was again followed by x1 going 0 and x1 going 0 . This particular diagram is nothing but drawn from the flow table that we, this is called the flow table, and this is nothing but drawn from the waveform that we had in terms of the transitions that are taking place. Now I will try to complete this. If there are certain combination of input changes, not just inputs but input changes that I have not considered, I have to consider them. I am considering only fundamental mode, so I do not consider this. I am once I am in my stable state here 1 0, I either go to 0 1 or 1 0. So this, but when I am in stable state 1 0, I will not consider this particular change. I will either consider 1 1 or I will consider 0 0 because I am in 1 0. Now when I am in 1 1, I can either go to, I will not consider this, I can either go to 0 1 or I can go to 1 0. So in this case 0 1 is already marked. Let me consider, I can even draw a waveform, but I do not have to do that. I know that if from 1 1 I go to 1 0, I should have my transient state should be 2, because once I reach this 1 0, then if I get again 1 1, if I can cycle through this, I will keep on getting my output to be 1. y1 was, after all this reflects that y1 is 1, x1 is 1 and x2 is 0. So any time I again go to 1 1, I should again produce an output of 1. x1 is anyway 1 earlier than x2 for this particular inputs. Similarly, when I am in stable state 4, I do not have to consider this, and when I am in stable state 5 0, I have to consider this, and you can see that this particular transient will also be 4. If I go to this, I can again cycle through this, and this will not be considered. So I first have to draw the waveform, identify the stable states, and once, or the total states, and once I have identified the stable states, then I can draw this primitive flow table. This particular table is the same as what I have drawn over here, and refers to the fact that I have 5 stable states. See, the only difference is, now once we have come to this particular stage, please remember one thing. When you talk in terms of the state machine for the synchronous, we have to have the state variables. It is the state variables which are going to be stored in the state register in case of the synchronous sequential machines, and I need enough state variables to bother about all these. But please remember here, these 5 states do not have to be just represented by the secondary variables. These 5 states are what we are here is both a function of the input as well as the secondary state. So now what we do is we go through a process of reducing this primitive flow table, and once we try to reduce this primitive flow table and then arrive at what are the secondary variables required.
So what do those mean? So one thing
Okay, what does it mean is, see, this is when I go from the input is 0 0, I am in a stable state 1 0, suddenly an input has changed. Okay, my input has changed from 0 0 to 0 1. If I look at this, take a snapshot of this, what is happening at this particular I was in, my input was 0 0 and suddenly my input is 0 1. If I now look at this, I am not in a stable state because this particular input change has not really resulted in all the changes that are going to happen. But temporarily, if we talk in terms of time, because after all the changes here, let us say of course this is a 0 delay time change because I have abstracted the delays out and put over here. So this delay, but this only this particular excitation will become the secondary variable only after a delay, and that may actually in turn also generate sometimes more changes in some problems. So this particular situation is indicated by a transient state. So it is not something which is stable, but it is transient, and that is what I am referring to this. The reason I am putting this to be 2 here will be clear that the process that we carry out, I actually would like that I immediately reach the stable state. I reach it as quickly as possible. I have no benefit in cycling through number of states. So with that intent of actually making these two same, I mark this as 2. When an input change comes, I should try to go to the stable state. We will see that how this works, and we will try to answer this question maybe in the next class, because once the procedure is clear, then this will also be clear that how it takes care of this. So what you raise this question again if things are not clear. So now we consider these stable states. Now what we do is we build a what's called a merger graph. Merger graph is nothing but compatibility between these stable states. What is the meaning of a compatibility? If I compare row wise, if there is no difference in the states in any of the columns, then those two rows are compatible. If I consider 1 and 2, they are compatible because this column is, there is a transient state and there is a stable state. So I will not consider them to be different as long as I have marked them to be the same. So this transient state 1 is, these of course is don't, right now I don't care here, so this can, these are compatible, this is compatible, this is compatible. Column wise, if every entry is compatible for all the columns refer essentially to all the input states. All the columns, then those two rows are compatible. So for, I identify all the compatible rows. So if you consider this, 1 is compatible to 2, 1 is compatible to 3, 1 is compatible to 4, 1 is compatible to 5. 1 is compatible to all the other rows. But now let us look at 2. I will not consider 1, I already considered it's not, it's mutual compatibility. So 2 is compatible to 3, but 2 is not compatible to 4. So when I consider 3, 3 is not compatible to 4 or 5, and when I consider 4, 4 is compatible to 5. Compatibility essentially refers to the fact that if I mark the same transient state, the final state that I am going to go to, if the same state is marked, then they are compatible. Otherwise the same states are written, they are compatible. Or if one is don't care, if I put a dash, then it is compatible. Don't care is compatible with anything. So in this case, this is compatible, this is compatible, this is compatible, this is compatible, and if all the entries are compatible, then 1 and 2 are compatible.
Why 2 and 4 are not compatible?
2 and 4 because 3, there is a transient state 3 marked, there is a transient state 5 marked. They have to be marked to be the same. Okay. So of course, there are a lot of design choices here. After all, the transient state that you mark is up to you. You could have marked this also 3. But that is going to create other complications because finally I have to go to stable state 5. I would be actually transiting through number of states that I don't need. So because I don't want that, I would like to go to quickly to the stable state. So I try to mark this to be 5. There are situations where we may have to do it and we will identify that. So once I do this, I draw this merger graph. The merger graph is nothing but a graph which contains all the compatibility edges. So the 1 and 4, so these are all the states. I have converted this information, 1 as an edge to 2, 3, 4, 5, 2 as an edge to 3 and 4 as an edge to 5. So I identify compatibility. Once I have done it, I actually am now trying to identify the secondary states. That is what I am trying to say, something which is. So what I try to now do is, I try to obtain find the minimum number of secondary states, and to do that I have to find a clique of this. What is a clique of a clique? Is a subgraph where all the nodes are connected to each other. Any subgraph which is a maximal, see what we are seeing is we do not want to consider those. So in this case 1, 2, 3 forms a clique, 1, 4, 5 also forms a clique. But I do not want, I also want to create a partition, implying when I am doing a partition I cannot afford to have the same node being present in more than one element, because these are all disjoint. Of course there are many algorithms to do it, it is a so but we can for this, as far as the purposes of this course is concerned, we will have small cliques and we can identify them. Otherwise in your algorithm course you will study more about the clique partitioning problem, which itself is a NP complete problem. So what you have over here is 1, 2, 3. So here we have one state that is identified A, and we have another state that is identified to be B. So I need to distinguish. So once I have formed, so I could have done this, the problem, the solution is going to be no different, and it's going to be correct if I had done 1, 4, 5 and 2, 3, does not matter, either way I can partition it. So I will reduce these 3 states to one state and these 2 states to one state in my what is called my reduced flow table, and this is the reduced flow table that I have. The one question that may come is, why are we talking of only secondary states here? The reason is, we are now, see, when we are finding the compatibility, we didn't bother, we only bothered among the columns, because an entry over here and entry over here will anyway be differentiated by the inputs. So when I am talking of my total state, I do not have to bother about distinguishing between 1 and 4. 1 and 4 are going to be distinguished by the inputs. That is why compatibility I only have to consider in the column, and that is the reason after doing my merger graph I get the states which need to be distinguished by only the secondary variables. Is this point clear? See, please remember one thing, when I am talking of, when I draw my timing diagram and when I draw my this is my stable state, I mean this is a total state, part of it is differentiated by the inputs, part of it is differentiated by the secondary state. So the differentiation that is done by the inputs is anyway going to be done, that is not, so that is why when I looked at the compatibility I only have looked at it in the column. So if these two are not to be differentiated in the secondary, using the secondary variables, that is what I am looking for, because anyway if you look at things which are let us say I merged 1, 2 and 3, but 1 and 2 and 3 are going to be, as far as the total state is concerned, they will be differentiated by the input state. So once I have done this, I will draw this reduced flow table. The reduced flow table is nothing but basically when you take this, so if there is any stable state, so if you are considered this 1, 2 and 3, 1, 0, 1 and do not care. So basically what dominates is 1, 0. 4, 4, 4, 4 do not care 4, so here it will have only 4 over here. Do not care 3, 3, 1, so it will, you will get 3, 1, and so in this manner I can draw what is called the reduced flow table. The implication is, once I have my reduced flow table, the implication is I need to have only 2 secondary states. When I say I need to have only 2 secondary states, the immediate conclusion is I only need 1 secondary variable. 1 secondary variable can distinguish, can be encoded in 0 and 1 and can get 2 secondary states. Now some more work needs to be done to actually, after all we are trying to make a machine which is completely deterministic. So I should also associate what is going to be the output with the transients. There are some states, okay, some of the transients have vanished here, okay, some of the transients are no longer here because of the merger, because I would like to merge as much as possible. What is the implication when I go from 0 0 to let us say 1 0, when I go from make this transition from state 1 stable state to stable state 2, in this mode I will not have any transients, I will directly go there. Okay, now but when I go from 0 0 to 0 1, I am going through a transient state. So I have to now define what is going to be my output at this transient state. Both ways, there are many ways of assigning it. Sometimes people assign starting from what the output was before, or sometimes, but the strategy that we can follow is we will try to make the outputs as early as possible. We will try to reach the output. That means I will associate the output that is there with the stable state, and I will associate an output of 0. What you should not do is, you should not, for example, here assign an output of 1, because the implication is it will generate a pulse, and completely an unwanted pulse over here. It will go through a transient state which actually gives you output of 1 and then go to 0. So you can either assign it with this or assign it with this, but anyway here we assign it with 0. And you have to also be careful, because this path, this is not the only path that is important over here. What is the other path that is going to come? I am not going to come from here to here because it is a fundamental mode, but I will come from here to here. I will come from an input 1 1 to 0 1, and I have to, so in this case 1 0 0. Now if I try to assign, for example, 0 based on this and 1 based on this, I will be in trouble. So that is the reason I just assign it based on what the output is going to be, earliest possible output. In this case the two places from which this transient comes is different. Of course here there is no such issue, here also there is no such issue. So I complete this, I made a reduced flow table, and now I have completed it, and now I am completely, I now just have to do the implementation, but before doing the implementation I had to do a state assignment exactly in the manner that we had before, and let us say I encode state A as 0 and B as 1 using the secondary variable. And once I do that, I have this particular table. This is my state A, this is my state B, and I replaced whatever, see, for example 1 3 and 2 are going to be replaced by 0 0 0 0 0, that is a state corresponding to A. 4 and 5 are going to be replaced by 1, so this is 4 4 5, these are all going to be replaced by 1. And now there is a simple combination logic design problem. I again reduce, just like in case of a synchronous state machine, and I derive, if I look at Z output is going to be 1 only here, and this is nothing but, this is my Y variable now. This is my secondary variable Y. So its Y complement x1 x2 is going to be, this is the only place where output is 1. So that is why Y complement x1 x2. And now as far as my this one is concerned, I can do a Carnot map minimization. In this case it is x1 complement x2, x1 complement x2, because I have eliminated Y, and in this case I eliminated x1, so it is Y x2 plus Y x2. A simple Carnot map minimization for 3 input variables. I am just considering Y as one variable, x1 x2 as another variable. So I have this circuit. Now let us see whether this circuit actually functions the way we want. So I will show a diagram of this. So what we have over here is this particular table generates a synchronous sequential circuit, and these are the equations that we had. So this is my x1, this is my x2, this is my, okay, Y is going to come from my output, and now I will have x1 complement and I have yes, so this is the circuit I have, and the important thing is the feedback. The feedback here is comes from this Y, and this is my Z that's coming. So let me draw this feedback path in red, just to differentiate between. Now let us say what happens. If x1 or x2, any one of them is 0, obviously output is going to be 0, there is no problem. When x1 and x2, let us say you are x1, x2, so you are 0, 0, then output is 0. Now when this becomes 1, 0, x1 becomes 1, x1 becomes 1, so this is 0, and x2 is 0, so this is going to be 0 because of the x1 being 1 first, and this 0, and x2 and y. What was the initial value when both these were 0? What was the value of this is z? What was the value of y? The value of y was when x1 is, when x2 is 0, value of y is going to be 0, irrespective of, because x2 comes at both places. So x2 is this particular path, it comes here as well as here. So this is going to be a 0 is going to come as a feedback. Now when this goes to 1, 0, so now what happens is x2 is 0, so this will remain 0, y will remain 0, output will remain 0, and now when I go to 1, 1, what happens? This 1, this y 0, and this 1, 1 is going to give me a z of 1. And now both are x1 and x2 is 1, 1, so this x1 complement is going to be 0, and this is going to pull it down to 0. So my y will remain 0. But so in this case I have produced an output of 1, but let us say I go from 0, 0, I go to 0, 1, instead of 1, 0 I go to 0, 1. So if I go to 0, 1, so x1 is 0 and x2 is 1, my output of course is going to be 0 because x1 is 0, output is 0, but y is going to become 1 because x1 complement x2, y will become 1. And this feedback y, when I become 1, 1, when I pass through this particular path 1, 1, so then what happens is this particular 1, this 1 and x2 1 is going to keep my y to be 1, and my output is going to be 0 because y being 1 means output is going to be 0. So what it does is for same x1 x2 1 1, this is going to be 1 here and this is going to be 0. I am going to get two different outputs, and that is essentially ensured by this particular feedback path. Remember that we are not providing for any additional delay, it is only the internal delay of the gates. Okay, so we will stop here, we will continue.